Hello, this time we're going to do an example of this use of the phasor representation of oscillating sources to solve AC circuits. This is the circuit we'll be looking at. We've seen it before, but this time we're going to use all of the shortcuts. First shortcut, draw the circuit, but use the phasor representations of the voltage and current sources. First step, redraw the circuit using these shortcuts. Things we'll need to know. We'll need to know the complex impedance of the capacitor. Well, it's a 200 nanofarad capacitor. The complex impedance of a capacitor is given by 1 over j omega c, and we're told that omega is 1 megaradian per second. So that makes the complex impedance minus j times 1 over omega c. And 1 over omega c is 1 over omega, 1 megaradian per second, times c, 200 nanofarads, which is 5. So minus 5j. We have to represent the current source in terms of its phasor representation. Now, for cosine omega t, we'd write that perhaps as omega t plus 0, just to make it clearer that the phasor representation of that is just 4e to the j 0, or in other words, just equal to 4. For the voltage source, that's 6 sine omega t. And we have to use the result here, that sine of theta is cosine of theta minus pi over 2. So we could write that as sine omega t minus pi over 2 and represent that in phasor form as, cosine. It's using the result sine x equals cosine x minus pi over 2. Write that as 6e to the minus j pi over 2, and that's the phasor representation of our voltage source. That means that the circuit now looks like this. Minus 6j. That's just another way of writing this. The phase angle is minus pi over 2, which means on an argon diagram it's going to be pi over 2 in the negative or clockwise direction. That gets us down there, 90 degrees. That point there is just at minus 6j. So the phasor representation of our voltage source is minus 6j. There's an impedance here, due to the capacitor, of minus 5j. There's a current source here with a phasor representation of 4. And there's a resistor with a resistance of 5. Okay, we've got two sources, so let's use superposition. First, consider just the current source. If I set the voltage source to 0, I'm replacing it with a wire. That leaves me with something which is a current divider. I can just apply the current divider equation and get that the current flowing through the resistor, call it IR, for just the current source, is going to be the current flowing into the divider, that has a phasor representation of 4, multiplied by the other impedance, minus 5j, divided by the sum of the two impedances, which is 5 minus 5j. That's the current flowing through the resistor, so if I multiply that by the value of the resistor, that will give me the voltage across the resistor due to the current source. And I've just done some algebra and working out the result here. The answer that I got was 14.142 at a phase angle of minus 45 degrees. That's the contribution from the current source. Now, the contribution from the voltage source. Well, if I set the current source to 0, that just means replacing it with nothingness. That leaves me with this circuit, and this is a potential divider. Follow through the potential divider equation. The input here, I've written it here as 6 over j, but 6 over j is just the same thing as minus 6j, since if I multiplied top and bottom of 6 over j by j, I would end up with that. J squared is just minus 1. That would just give me minus 6j. So voltage as a phasor representation is 6 over j at the top of my potential divider. This resistance is 5 ohms. This resistance is minus 5j. Potential divider equation would just give the contribution to the output. I'll call it V2. This is V1, the contribution from the current source. The contribution from the voltage source is 6 over j times 5 divided by 5 minus 5j. That's the sum of the two impedances in the circuit. And then it's just a bit of algebra through that, and I end up with this result here. The second contribution to my voltage, 3 times root 2 times e to the power of j of pi over 4, which I sometimes write as 3 root 2 at minus 45 degrees. I can then use superposition to add both of these up, noting that 14.142 was actually 10 times root 2 at minus 45 degrees. Adding V1 to V2 gives me 13 times root 2 at minus 45 degrees. For my total output as a phasor. That's the phasor representation of the voltage across my voltmeter in this circuit. If I want to convert back from that phasor representation to the actual waveform that the voltmeter would see, I just have to multiply this phasor representation by e to the j omega t, take the real part, and I would end up with that. 13 root 2 cosine omega t minus pi over 4. When you analyze these circuits in the simulator works in phasors the whole time. So it will just give you the phasor representation of the voltage across the voltmeter. In this case, we'd just see this. 18.38, which is 13 times root 2, and the phase angle minus 45 degrees. If you were to plot this on an Argand diagram, it would be there, since that's exactly what this plot here does. The only real difficulty in analysing these circuits is the fact that we have to deal with complex numbers, the phasor representations of all of the voltage and current sources and all of the output voltages and currents. So all our mathematics is now complex. But apart from that, all of the techniques that we used for linear circuits in DC analysis can be applied. We'll see a few more examples in the next videos.